Okay. Are there any general questions? Okay, so yesterday I sent out an announcement. The exam grades were posted, and I give you about sort of 10 days to come to discuss with me if you want about your exam results. Okay, so my office hour is one venue to discuss, and just make sure you realize Thursday's office hour still remain 1 to 2 p.m. But Tuesday's office hour move up 1 hour, 12 to 1 p.m. to accommodate some student who say 1 to 2 p.m. office hour bumped into their one of the classes. Okay, and if you want have a different time, just drop me an email. I can see if I can make that available for you to discuss your results as well. Any question? Okay. Exam solutions will be posted. I have one student still need to complete his exam, and right now it's scheduled sometime Thursday afternoon. So after that is done, I will post the solutions. No questions, so let's come back to our where we left the last class lecture. So last lecture, we discussed the first basic common emitter amplifier. In this configuration, we discussed how to simplify the full circuit into its AC equivalent circuit, including the bipolar junctions, transistors, hybrid pi model. And from this circuitry, which you should not be too sort of afraid, because this is one of the typical circuit you would see in 306 context. Then we derived a number of quantities. Okay. And now, are there any questions for last lectures, the material? If no, so let's go to the next page. Okay, this is I also informed you the lectures notes of chapter 6 is updated. So I will point out to you a few parts which is updated. Okay, first, I will let you know the updated part is this part. So it's a new page 10. Okay, this one. Okay. So one of you asked, how do we handle the bipolar junction transistors, and how different this is from the between the base and emitter is a diode, and so on and so forth. Okay, basically, I said last time is one model we introduced in chapter 5. It really is a full active mode that's works for the DC circuit. That's here I create a new slide, the note, which is put on the left. So here I use the NPN transistor as a example. So the left side repeat what we said from chapter 5. Okay, on the full active mode, and between the base and the emitter, you have a PN junction diode, so it's represented by a diode symbol. But then from between the collector and emitter, since the current IC is proportional to current IB by beta coefficient, so really says that IC can be modeled by a dependent current source. The dependence is beta times IB. Whatever current IB amount you have here, then this amount of current will be beta times IB. Of course, this is only true on the full active mode, right? So most of the time in chapter 6, we analyze in this state, in this mode. So that's that model applies. But that's a DC circuit. For AC circuit, for amplify small signal amplification, so basically we have a different model. We model is called the hybrid pi model. So we describe the derivation where this model was derived mathematically, basically between the base emitter, the voltage VBE and current IB is exactly related by an Ohm's law relationship to the resistance R sub pi. So this section is R sub pi. Another section, okay, is dependent current source IC1. I call it IC1 beta 1 because if you neglect the early voltage effect, then this IC. But we said last time, if you want to include the early voltage effect, really outside here is the IC. So this part is one portion of IC. I named that as IC1. So indeed, this part is dependent current source is IC1 equal to beta times IB. But then there's another current is VCE divided RO. So we discuss on this equation. Okay, so that's why we introduce another output side resistance RO. And here, you can say, well, we make all the different effort to derive the model for the DC circuit and the model for the AC circuit. Are there any connections? That's what the reason I put these two models to you is to try to make the connections. Okay, the connection is this diode generally is true. Okay, under DC condition, what we approximate this diode is just once it's on, it's just VBE equal to VBE on. So we say this is V gamma or VBE on. We neglect that small resistance. Okay, so this VBE equal to VBE on. Well, this diode under AC condition, what do we treat? In AC condition, then we will short that V gamma, but retain that resistance R. That resistance R is renamed as R pi. So you can see this guy came in naturally from this diode model when you talk about the AC equivalent circuit. And this dependent current source is still the same dependence as previous one, because this dependence is for full circuit, then it's the same, a full signal, then it's the same for the AC signal. Okay, so this, but only modification is this only represented part of a current IC. So I call it IC1. Okay, the true IC is really outside. Okay, small resistance RO, not small resistance RO, resistance small RO outside here. But nonetheless, base current plus the full collector current equal to the full emitter current. Okay, so this is the Kirchhoff current law consistent for the full signal, the DC signal, as well as for the AC signal. So that helps you to come a little bit more easier, natural, where the hybrid pi model came from. Next is we go to the example. Okay, so this is illustrated here. So this is an example I take out as the textbook is exercise 6.3. Okay, the left is the circuit. The upright is just the circuit's parameter beta equal to 90. This is the PNP transistor, so it's VEB on equal to 0.7 volts. And early voltage effect, the early voltage is 120 volts. And we bias the voltage, here is negative bias, but the magnitude of bias voltage VC is equal to 5 volts. Okay, the other bias voltage is a VBB. Okay, that's a 1.145 volts. Two resistance value given RC and RB. Okay, how do we solve this circuit fully? Okay, we have to know where the DC bias is at, or question point. So we want to find a DC solution. So how do we handle DC solution? So the AC source should be deactivated. So AC source should be set to equal 0. So once at this AC source, AC equivalent circuit, then we can calculate first around this KVL loop, voltage VBB equal to voltage drop VEB drop down, and another voltage drop at the resistance RB. And that full loop KVL can be re-expressed to calculate the current in the base. Base current at question point equal to VBB minus this voltage and divided by the resistance RB equal to this current. So the current IB goes into this direction and back to power supply. And you substitute the value of VBB, and VB on the 0.7 volts, RB is 50 kilo ohm, and you came out with a 0.089 milliamps. Okay. And we know, or we assume this works in the 4 active mode. So then the collector current equal to beta times base current. So its beta is 90 times this IBQ, is this current. Then you get a 0.8 or 1 milliamps. Okay, so the 90 times larger. And how do we figure out the quiescent point or the voltage drop between the collector and emitter, which is VEC at the quiescent point? So you can see another Kirchhoff law. Okay, basically that voltage plus this voltage equal to power supply voltage VCC, or VECQ equal to the power supply voltage. Subtract the voltage drop at the resistance RC, it leads to the recipe here. So the VECQ equal to VCC minus RC ICQ. And we know the value of bias voltage is 5 volts VCC, and we know the resistance is 2.5 kilo ohm for RC, and current ICQ is 0.8 milliamps, and you get this voltage drop is 3 volts. Okay, and the 3 volts is almost like a little bit more than halfway off between the 0 volts and VCC. So indeed, bipolar junction transistor is biased in the middle of the 4 active mode. This is a DC part of the calculation, and you can say, why we need this calculation if we want to work out the AC part of circuit? Well, you need the bias voltage, bias current ICQ, okay, this Q. So next slide says, okay, AC solution. So this is coming back to the original circuit. Original circuit, when you work on the AC part of the circuit, you deactivate the DC source. So you deactivate VVB. So the negative side of VS is grounded. Negative side of VS is grounded. Okay, and then this positive side of VS is here, and resistance RB is here. All right, and this is the base. So this is the base, and this emitter is grounded. Emitter is grounded. Okay, output is taken out at the collector. Output is taken out of the collector. So you identify the 3 locations: the base, collector, and emitter. Between the base and emitter is resistance R pi. Between the collector and emitter is dependent current source in parallel with a resistance small RO. At the very outside of the transistor, then from this point to the ground is equivalent from this point to the ground, because VCC is grounded as well. So it's RC at the very, very outside. Okay, so that's the AC equivalent circuit, how we obtain that. So, and then the resistance is, this is a PNP transistor, so it's a VBE is important. So the positive side of EEB, or called V pi, is at the emitter, and negative side of this voltage V pi is at the base. So the V pi is the polarities of plus minus. How about dependent current source direction? It just follow this arrow. So this arrow says, well, the current flows from emitter and to the base, emitter to the collector. So this emitter to the collector. So the dependent current source is pointing upwards. That's how we simplify the full circuit to AC equivalent circuit. From this circuit, we're able to continue to calculate the AC part of solution. So first is that we need to calculate the small signal hybrid pi model parameters, because those are 3 quantities: R pi, GM, and RO. And by definition, R pi equals to VT, thermal voltage, divided by the base current at the quiescent point, and which can be also calculated from the collector current. Okay, you modify that factor of beta, and numerically it turns out to be 2.92 kilo ohm. You can also calculate the parameter GM. Okay, basically this quantity GM. And it's ICQ divided by thermal voltage VT. And you complete this calculation. ICQ is 0.8 milliamps. VT, V thermal is 0.026 volt. End up with 30.8 milliamps per volt. How about this? Okay, resistance RO is early voltage divided by the quiescent point collector current. So you substitute the values, you get 150 kilo ohms. So we found the values for R pi, GM, and RO once we know the quiescent point, okay, collector current. The next quantity is interesting is what's the input or equivalent input resistance seen before the resistance RB. So it's here. So basically looking from here into this portion of the circuit. So what do you see? Obviously it's RB in series R pi. So the input resistance Ri equals Rb plus R pi. And we have those values because we just calculated R pi, 2.92 kilo ohm. Then total together is 52.92 kilo ohm.
What's VT again?
Thermal voltage 0.026. Basically, right. Yeah. Chapter 1, right. So once we find out this equivalent input resistance, okay, actually here you don't need it further, okay. So we have the voltage Vs. How much voltage is actually loaded to this resistance R pi or the V pi? Because once you know how much voltage you get to V pi, you put in here, you can calculate the output voltage. So how much voltage we can get out of V pi from Vs, and simple voltage division from 3 to 6, we can figure out this. So V pi is voltage division from Vs. The division ratio is R pi divided Rb plus R pi. The only thing is make sure you don't miss the sign, because the Vs is a top is plus polarity, bottom is negative polarity. How about V pi? Is opposite defined. Bottom is positive polarity, top is negative polarity. So there's minus sign here. Magnitude-wise, it's voltage division, but polarity you have to put in the minus sign here. Very important. Don't mess up with the sign or make mistake. Now we know how much V pi we get out of Vs, so we can substitute into here. The next we calculate how much this current produce how much voltage drop between the top and the ground. So you have current coming to this parallel combination for the small RO and capital RC, and that's the voltage drop VO. So the VO equal to GMV pi times parallel combination of RO and RC. Okay, so we need to figure out the parallel RO and RC, and by the parallel combination formula, RO is 150 kilo ohm, RC is 2.5 kilo ohm. So product of 2 divided by sum of 2 gives you the parallel combination value is 2.46 kilo ohm. So basically you calculate this quantity. And now we're ready to figure out what's the small signal voltage gain. Okay, so the VO equal to GM V pi times RO parallel to RC. And V pi is derived out of the Vs. You substitute this equation into V pi here, you get a last expression. And your last expression says from Vs, you end up how much you get a VO. And this ratio defines the small signal voltage gain. Okay, so you move Vs to the left, and the rest of the expression is the small signal voltage gain. So it's here. So we calculate the value of a GM, value of RO and parallel RC is 2.46 kilo ohm, m times this ratio is 2.92 kilo ohm divided by 52.92 kilo ohm. It end up the gain magnitude-wise is 4.18, but the sign with a negative sign. Negative sign says the output voltage and input voltage or source voltage, the polarity just flip. Okay, when input is on the positive cycle, output is just on the negative cycle. That's just the physical reality, but doesn't impact any performance of this common emitter amplifier. So
I have 2 questions.
Yes.
First, what is AV again? Is that an average?
No, it's called the small signal voltage gain.
Okay.
A is the gain. The voltage subscript says this gain is a voltage gain. And if you say AI is a small signal current gain. So this is a small signal voltage gain. It's AV.
And why did we need V pi again?
Let's see. You want to complete the calculation. How much voltage I produce VO? You need to know this amount of current times this resistance, right? And this amount of current is a dependent current source is GM times V pi. If you don't know the amount of V pi, how do you determine the final voltage?
Oh, I see it now. I didn't see that earlier.
Okay, just pay attention to every step we reach to the final, right? Just this is my standard equation. How much voltage VO you produce really depends on how much V pi you get from the source, right? And how much V pi you get the source, you have to go one more step early to say, this amount of V pi I get out of this source voltage with VS. So it's just one step by one step substitution, okay? Another quantity is a small signal, well, not small signal, equivalent output resistance seen really at the output side. So it's a RO as indicated, you view inside. Okay, calculate this as output resistance. And this circuitry, you're looking for the equivalent resistance RO, but this circuit contains an independent source VS. Whenever you calculate the equivalent resistance, you have to deactivate the independent source VS. So in this step, you have to deactivate the VS. And once you deactivate VS, and you have RB just simply parallel with R pi. And this side of the circuitry is not powered by any source. Do you have current in this part of the circuit? You don't have. It's a dead end current. So there's a current is zero. Once the current is zero, then voltage drop across the resistance R pi will be zero. So you determine once you deactivate source voltage VS, V pi will be zero. Once V pi is zero, then the amount of dependent current source will be zero. So this becomes open circuit. So once open circuit, what the output resistance you see here is simply the parallel combination for RO and RC. So just output resistance is a small RO parallel with RC, which we calculated previously is 2.4 kilo ohm. So put it here. All right. So this is the small signal calculation. And last bullet, I just remind you, okay, the superposition principle, what it means. This voltage, this is physical circuitry. Between the ground and this point, the voltage, if you fully measure the voltage or using oscilloscope, this is full physical voltage. And this voltage contains a DC portion as well as an AC portion. That's what the superposition principle says. So the full output voltage VO equals the DC voltage VECQ and plus small VO. And small VO, by this, I can re-express as the small signal voltage gain times the small signal source voltage at this time. So to fully answer, so exactly what's the full voltage at the output, then you have to complete the last step. Any question? Okay, so this is.
So I have a question.
Yes.
So for the full output voltage, in this kind of setup, will that always be the equation for it?
For the last bullet, the equation?
Yes, the full output voltage.
Okay, good question. For this particular circuit, yes. But quickly, I will lead you to the next circuit, okay? So, not necessarily circuit. So if you want, I can quickly just go to one example later, I will comment. How about the circuit, the previous is kind of right out of the collector, but that just amplifies itself. And you build the amplifier, well, you can say for the fun, I can build an amplifier, but that's not where you need it. You need to drive the amplifier result to your load resistance. You drive load resistance usually is you carry the AC signal amplification. You don't need a full signal. So you need a capacitor to block the AC, block the DC. So the true output is end up at the load resistance. Okay, whilst using the coupling, capacitor coupling. So if you can see my cursor right out at the collector, then you can talk about, if you define this as your voltage, output voltage, you measure here to the oscilloscope, there is a full output voltage. You have to include the DC part. But if the scope is not at here, it's at the very last part, it's above the load resistance, then you block the DC portion. You only have a small VO there. Okay. Yes, it's dependent on the exact circuitry and what the factors are involved. Okay. So that last part is just saying for this particular circuit, then you have to include the VEC Q. But for some other circuit, and you depend on where the final output is, then you have to decide whether the DC part is filtered out or not.
So would we generally need the Q voltage to figure out the full output?
If the full output is not filtered out by any capacitor, yes, you need it. But it's the final output is before you reach the final output, you put a capacitor, you blocked the VCEQ, then you don't need the DC portion. Okay?
Okay.
Yeah. It depends on where is your ultimate output location is. Okay.
Professor,
Yes.
the slide says that the resistor RE is added to stabilize the QPT. Is that mean that there are circuits where there is not a stable QPT?
Can you refer which page slide?
The page you were just on.
The this. This.
I know the page you were on. I didn't catch if you scrolled up or down, but
can you recognize which circuit? That's only two
no.
circuits I discussed, right? One is on the left. This. Which circuit you? I only mentioned that two circuits.
The emitter, page 18.
18. Okay. So what's your question?
Sorry, I guess it's 19. It must be the next one then.
19? 19 is an example of the formula, right?
Was it that? I guess it's...
What's your question?
It must be frame buffering for me because I'm not.
It's 20. It's page 20.
Page 20. Page 20 is a new circuit. I have not got into that.
So my question isn't about the circuit on page 20, but rather the statement that they're saying they're adding resistor RE to stabilize the QPT.
Yes.
Does that mean that all the previous circuits had unstable QPTs?
Exactly. Okay. From what we learned, or from you're supposed to learn from the chapter 5, that previous one is amplifier circuit, but everything designed perfectly, it may work, but it's not good design. If you learn from chapter 5, you know this is not a bias stable circuit. It kind of a circuit can work, but hopefully nothing kind of a sensitive to the beta variation. So it's just a theory. Okay, how do we, if you're given this circuit, how do we analyze that? But is this a circuit good circuitry? No, you have to come to the next one.
I'm sort of confused then of what does stabilize mean for QPT? Does that mean QPT is constant regardless of other factors in the circuit?
I'm not claiming it's constant. I'm only saying if the variation of the beta, if beta is not 90, maybe drop to 50, or beta change to 120, or resistance value varies somehow by some ratio, then the shifting of question point is very, very little. If a certain condition is satisfied, this is all in chapter 5. You really need to review chapter 5.
So the reason I'm asking is I read chapter 5 and I found this quite confusing. So you're saying that the QPT changes with what? The resistance?
Variations. Okay, at least this one we demoed in chapter 5. If a beta changes value, then this is not sensitive. If a certain condition is satisfied. You don't have any sort of a vague memory?
No, I did not understand that part. That's why I'm asking.
You don't understand, then you should keep up. Okay, let's just go back to upload the slides for chapter 5. So it's while running into chapter 6, if you have any question, you say you don't understand, you better ask me sooner, not carry that uncertainty into the next chapter. Okay, and here, really, once we get to chapter 6, I really assume you digest the material in chapter 5. What's that?
Actually, I was a little bit confused with chapter 5 myself, and I was hoping chapter 6 would be able to clarify that.
No, okay, everything is built up on the previous one. You don't understand previous one, you just add up the confusion. So that's like the chapter 6 can just maybe reinforce the concept, but all the principle laid out is chapter 5 is chapter 5 subject. It's DC circuit. Okay, so let's go to okay. Bipolar junction transistor biasing, chapter 5. And that circuitry is not stable. We said the reason, slide 30, 31. And then the next one is very important. So the voltage divider biasing and bias stability. Okay, this circuitry is exactly what this circuitry, okay, on the right side. Okay? And the next page, we analyze. The blue, once certain conditions is satisfied, then we say the question point means the location of the collector current, and the VCEQ is stable, means not much dependent on the change of the beta. Okay? Any questions? Chapter 5, slide 32, 33. Lay out all the basic principles. Why we need resistors RE. Okay, or what's the role played by RE. Okay. And of course, you stick RE doesn't mean you will make that happen, but you need a satisfied condition. That satisfied condition is a bullet in the blue, and then the bullet in the red. You have to satisfy something like that. And that says implies in chapter 6, the transistor the circuit component will be selected such that those conditions are assumed to be satisfied. Or then there will be a homework problem in chapter 6. Say you have to make sure when you design a transistor amplifier, that condition are satisfied. It's not automatically landed to that. It's just that you have to properly select the value of R1, R2, RC, RE, and make that happen. Any question? Okay, so conceptually, this is a subject we went through that in chapter 5. If you're not familiar with, then probably you have to go back to chapter 5 to get slide 33 and then revisit that part. So next, situation, that's what the next slide, page 30, is what we're dealing with. Basically, this says that the DC part of the circuit, we insert the resistance RE and try to stabilize the question point, means that if any component parameter, the beta shifted, say it's not a 90, get it to 100, 20, and so on and so forth, then you collect the current and the voltage VEC at the question point doesn't change. So that's the purpose. So that's the biasing circuit. We would like to go this route instead of the previous one. That simply says borrowing the knowledge from the chapter 5. But once you put in the RE, we analyze this full circuit back in chapter 5. But what you want to know now is, well, in chapter 6, we want to know what the AC equivalent circuit behaves like what. So the next is, once you add the resistor RE, then you can see, okay, what's the effect on the AC equivalent circuit. So you short the capacitor for AC signal. So this V of S, R of S is here on the input side. Okay, once you get here, it's called, we call the input voltage to your AC transistor circuit. So the input is viewed here, that's V in. And this is, say, what do we see AC equivalent circuit? In AC equivalent circuit, you short VCC because this is a DC source. So once you short VCC, this point really touch to the ground. This point to touch the ground is equivalent to say R1 is parallel with R2. So R1 parallel with R2. After R1 parallel with R2, you get this point, that's your base. So that's your base. Output is at the collector, output is collector, and through resist RC gets to ground. Through resist RC gets to ground. And between the base and emitter is R pi, between the collector, emitter is dependent current source. You can see where that additional RE resides. It resides between what? Emitter to ground. So it resides from emitter to ground. That added resistance in AC circuit is here. Well, you can compare this circuit previously. If we don't have RE, that's a circuit to the left, the example we just went through. But if you add an additional resistance to perform a biasing stable, okay, the property, then you have extra resistance RE here. That's the complication. Okay. Now next, let's see how complicated it is. So the circuitry, I will still display to the left screen. On the right screen, I move to the next page. Means the derivation. Okay. So the common emitter amplifier with the RE resistance, the full-blown analysis. First, we want to answer the question of input resistance, because without the input resistance, we don't know the source voltage, how much is actually can be loaded to the transistor amplifier. So we need to find out the resistance, input resistance RI, viewed from here, or viewed right after capacitor CC. Then this is a full circuit, a sequence circuit. Then I'll do that in two steps. First, I'll figure out the equivalent input resistance viewed after the combination, parallel combination of R1 and R2, after here. So from here, I viewed into this circuitry. That's the location I view the equivalent input resistance. RI is B. RI means equivalent input resistance. B means at the location of the base. Okay, viewed at this location, basically between this point, base, and the ground. So what do I see? Equivalent resistance. And equivalent resistance definition is the voltage drop between this point to this point divided by input current. So it's RB equals V in divided IB. That's the definition of this equivalent resistance IB. And these have the two quantities, V in and IB. So what's V in? So V in is voltage labeled here, but then this voltage is the same voltage, okay, at this location to that location. And that V in contains what? Two steps. One is voltage drop at R pi, means that's this part. Another voltage drop is at the resistance RE. So that V in equal to V pi, and V pi equal to R pi times IB, base current. And plus, what's the voltage drop at the resistance RE? Then at the resistance RE, you have two contributions of current. One branch coming from this base current IB, another contribution coming from the collector, which is beta times IB. So the full current, emitter current, is the sum of this current and that current. So it's sum of this current, that current is just a basic emitter current is 1 plus beta times IB. Right? And input current, you view it from here, it is base current. So that the ratio defines the input resistance R of IB. Final expression is R pi plus 1 plus beta times R of E, capital RE. And here you can say, all right, if you just glance this circuit from 306 kind of a circuitry impression, and you may say, if I view it on here, it looks, if asked what's the equivalent resistance from this point to this point, obviously it's R pi in series RE. So you may simply say this is R pi plus RE, right? Well, that's if you don't have this dependent current source. If you don't have a dependent current source, indeed this equivalent resistance should be R pi plus RE. But since you have another branch current contributed into the voltage drop at RE, so that's a factor 1 plus beta factor comes in. The thing is, this is the effect is called resistance reflection rule. What does it mean? It means the effect of this resistance RE is multiplied by factor 1 plus beta. Why? Because the current, passing through resistance RE is through by the current I of E. And I of E is 1 plus beta times I of B. So there's this multiplication factor here. So this RB is R pi plus 1 plus beta times RE. Once you find out the equivalent resistance viewed at this point, you make a one step back. You view the before the parallel combination of R1 R2, then just simply R1 R2 parallel with this R of IB. R1 R2 parallel with RIB. So you identify the equivalent input resistance right before R1 parallel with R2. Once you figure out this equivalent resistance, you ask how much voltage I can get to this transistor amplifier circuit V in out of Vs is a voltage division relationship. 306 knowledge help us to identify that. So that's the reason the input resistance bullet, all the purpose you calculate this is try to answer the last expression. How much voltage V in I can get out for source voltage Vs. But once you get this, then we can carry out next calculation. Next calculation is I want to find out the small signal voltage gain or the A of V, this one. Then I need to find out what I can get from the output voltage. So this output is measured after resistance RC, and this current passing through the RC. So basically, it's this amount of current beta IB times resistance RC is the voltage you will measure, except the polarity, because the current goes IB here is going down. If you look in this, the current is pointing upwards, but the voltage defined as VO to the ground. So there's a minus sign here. So the output voltage VO equal to minus the dependent current source amount beta IB times resistance RC. Then how much the base current small IB I can get? Well, we just have this expression. When we define the equivalent input resistance R of IB is linked to the current IB. So IB will be really equal to V in divided by R of IB. So I can replace this IB by V in divided by RIB. And V in is related or derived out of a Vs. I have another factor here, voltage division factor. I can express the output in terms of input source voltage Vs. Okay. And finally, what's the small signal voltage gain? From the source voltage to output voltage, that ratio defines that the small signal voltage gain is V out divided by Vs. It's just rest factor here. So this rest factor is the same as this rest factor, except that I put in the exact expression of RIB with this one into the denominator. So this way, I formally derive the small signal voltage gain, capital AV. And now, because this 1 plus beta factor is very big, it's 100 times RE. And then this, in the first denominator, the second term magnitude can be made, if we choose RE, reasonable, size, then the second factor can be overwhelming the first factor. So the first inequality can be satisfied. Okay, so if under some conditions, so we know the magnitude of RE and magnitude of R pi. If this relationship is satisfied, then we can drop R pi. Once we drop R pi, there's 1 plus beta. And beta is much greater than 1. So you can drop the 1. So in the denominator, you have a beta. Numerator, you have beta. These two beta cancel out. So the small signal voltage gain does not directly depend on the beta. So it's the same concept. Okay, we verify, demonstrate. Okay, the question point is insensitive to variation of beta, and here we're saying that conclusion was drawn for the DC circuit, and the similar conclusion we can draw for AC circuit. Say small signal voltage gain really not dependent on much on the beta value. So the beta you vary from 90 to 120 to 150. Well, it doesn't affect your small signal voltage gain much. And furthermore, this small signal, this source resistance usually is very small if you have a good voltage source. And then if the input resistance is fairly large, and the second inequality can be easily satisfied, and you can drop a V sub S as well. Once you drop a V sub S, Ri just cancel with Ri. Numerator, Ri on the numerator, cancel with the numerator, Ri on the denominator, cancel out. So what do you end up with? The small signal voltage gain just approximately equal to the ratio of resistance RC and RE. This is demonstration of this. Once you put the resistance RE, okay, if certain conditions can be satisfied, then the small signal voltage gain really not much dependent on the question point value, okay, or the beta, and so on and so forth. Really, it just determined externally by the ratio of the two resistances. Basically, if these two conditions are satisfied, okay, the small signal voltage gain is just a ratio of RC over RE. And if you change the resistance value to be a factor of 10, then you get a small signal voltage gain of factor of 10. Okay, that's good. And here I just want to reinforce the things I mentioned. This small signal voltage gain AV really defined as the final output to the source voltage V sub S. But if you so this output voltage all the way related to the input source voltage, that relationship is voltage gain defined AV. But if you define voltage gain is V out here, depends on how much I load into the transistor amplifier V in. So if you define this ratio as your small signal voltage gain, distinguish that from the previous definition. So I put the prime there. So what's this quantity? And from this equation, you can see it just this factor. Okay, it's that voltage gain. And this factor is written here. I put in the explicit expression of R sub B into here. Okay. Any question? So this is the role played by the resistance RE. Okay, once you choose this, then the output voltage is simply related to input voltage by the ratio of RC and RE. Okay. Next, so how do we figure out the equivalent output resistance? Okay, viewed from here into the circuit, viewed from here into the circuit. When we do the output resistance, we want to do the output resistance for this whole circuit, equivalent output resistance whole circuit. But then when you want to figure out the output resistance, equivalent resistance, you have to deactivate the independent source. So the V sub S should be set equal to 0 because the voltage source deactivate. Okay. So once you deactivate, then let's see. Okay, still the circuit is complicated. Okay, even it's a 306 circuit, you have to be a little bit careful. And okay, generally speaking, you have to add a source voltage to calculate that equivalent resistance. But here, I also point out there's a shortcut way to to find out this RO. The shortcut way is, as I illustrate here, once you deactivate the V sub S, R sub S is parallel with R1 and R2, right? So this resistance is parallel with this resistance. And here on the right, I renamed that called R of S prime. So it's R of S parallel with R1 and parallel with R2. So you visualize this part of the circuit is replaced by a single resistance R of S. And this single resistance R of S actually is in series with what? R pi. Okay. This R pi, this amount of current passes through R pi. I can visualize this current IB not pointing this way, but how about the minus IB pointing out? Where this current coming from? Because I deactivate this S, and this current coming from the what? Beta IB. So beta IB coming in, split into a portion goes to RE and portion go to this way, minus IB, and end up here. And here is current division issue. Okay, current division issue is how much current I get from out of this way, out of total current, input current. So it says minus IB, I put minus sign on the other side. Total current is beta IB, and there's a factor determining that current division is this branch of resistance RE divided by the full resistance RE plus R pi plus RS prime is in the denominator. So this is current division. How much current I get in this branch out of this coming in current. So I derive this equation by current division. Left side is I sub B. Right hand side also there's a related to I sub B. If I move I sub B from the right side, this part, to left side, I can factor out I sub B. I can factor out I sub B with one rest quantity is 1 plus this quantity, which is non-zero. The product I sub B to the rest non-zero term must be 0. I must conclude the solution must be IB itself be 0. So that's why I can determine IB itself to be 0. Even for this circuitry, it's not obvious, but I can step by step still work out current IB is 0. Once current IB is 0, then this dependent current source is a break, open, then the output resistance seen from here is RC. So this RO equals RC. Okay? This is much extension from the previous circuit. The previous circuit is saying we know the equivalent resistance is this guy. Then we say if I deactivate this S and there's no current here, that's what we conclude. Okay, but here even with the emitter resistance RE, and we still conclude this amount of current, base current is 0. Okay, but you have to go through even more convincing step by step derivation to convince me that indeed is the case. Okay. And last bullet is answer the issue of the AC load line. Okay. We know load line is related to the current IC versus voltage VCE. So the current IC is the voltage VCE. Basically, it's a KVL, but it's AC KVL. So the voltage between VCE here is the voltage, and this voltage equals the voltage drop at the output voltage here VO subtract the voltage drop at RE. So this VCE equals output voltage minus the voltage drop at RE. And VO we derive this VO is just this current source multiplied the resistance RC is this plus the sign is negative. Take care of the sign. And the second IE, I can convert it into relate to the IC by this factor. And shift out IC out, and then the coefficient in front of by the reciprocal is AC load line slope. Okay. So this AC load line slope is different from did I have the AC load line slope? I didn't derive the previous one. Okay. Any question? So the RE, okay, effect is coming in to affect the AC low line slope. Any question? Well, here we say we introduce resistance RE to stabilize the crescent point. And then one benefit, we can see that means the small signal voltage gain is just simply determined by the ratio of external resistance RC over RE. But if we want the small signal voltage gain be large, what choice we can make? You can make either RC large or RE small. Okay. Generally speaking, we don't want a large RC because it kills much voltage because Ohm's law. Okay. So you may say, oh, I want to reduce RE. On the other hand, when you reduce RE completely, it's as if you remove the RE. But once you remove RE, then you defeat your purpose. Originally, you add RE to stabilize the DC crescent point. But that's from the DC consideration. But AC consideration, you want a small RE. Seems like two requirement considerations are opposite to each other. How do we solve this conflict? Here is circuit. The circuit is you introduce a capacitor to bypassing the emitter in AC circuit. So you put a capacitor CE to bypass the resistance RE. And here this illustration is we're not fully bypassing the total RE, but only a portion of RE, as if I indicate there's a portion of RE is RE2 here. This part is the bypass in AC circuit. So in DC biasing, full amount of RE plus RE2 will be the true RE responsible for DC biasing. For AC circuit, RE2 is shorted. So RE2 is shorted, but RE1 remains. So the previous circuit can redraw, then RE is not only a portion of original RE is RE1. So this circuit is the same as here, except RE is partially shorted to only keep the RE1 portion. The rest analysis carry the same. Any question? Okay, so let's just move. Yes, that's circuitry. Next circuit, is next slide is a very important concept for the low line, and then symmetric swings, the issues, very important. So go back to the original circuit. If you neglect the capacitor effect, not let it open, you have a DC biasing circuit, and you can calculate DC low line. DC low line is a DC voltage VCE related to the DC current IC. So this plus voltage minus voltage is total voltage difference between top and here. Then you subtract the voltage drop at resistance RC and RE1, RE2, and you get the KV out here. And here, if we make approximation, the current IE and IC are approximately the same, then the low line equation is simply this expression. So the resistance RE, R2 play a role for the low line slope, as indicated in this in this diagram. A low line slope. Low line slope. Okay, I want to make the cursor out. Slope is determined by the contributed from RE1 as well as RE2. How about the AC low line? And then previously we just derived the AC the data equation. Previously borrowed this equation, AC low line, and then now the RE is contributed from the RE1. From here RE1. So it's basically this voltage amount plus this voltage amount gives you this voltage amount. And the current in this branch and current this branch, this IE and IC approximately equal, and you get the AC low line. So the resistance, RE2 is shorted, only left with RE1 contribute to the AC low line slope. So this AC low line slope, reciprocal wise, is RE2 is removed. RE2 is removed, the denominator is smaller. Denominator is smaller, slope is steeper. So the AC low line just queued up, is steeper. So this AC low line. So AC signal will swing around the crescent point. But around the crescent point, they don't swing along the DC low line. They swing along the AC low line. That's what it's on the line. So the amount you can vary the current in this side is related to amount of current variation, variation up and down here is related to amount of voltage variation on this side. When it's IC, when it's a VCE, you derive AC low line. So the change of a VCE and then change of IC is related by this factor RC times RE1. And full signal equals the sum of the DC current plus AC current IC, and DC voltage VCE plus small signal VCE gives you the full voltage, the concept. Second, the issue next one is very important. So this symmetric swing, what does it really imply is we want a linear amplifier. We don't want a distortion. Okay, so what kind of distortion we need to worry about? Okay, so the first bullet says, for linear operation amplification, we have some requirements you need to consider, satisfy. One is the collector current IC, the full collector current IC can swing down and can swing up. But when the swing down, then it must be above zero, above cutoff. So you may say the full current cannot touch zero. But if you want to put some margin, you may set some minimum limit, IC minimum, which is above zero. So you have to avoid running into cutoff. So that's if the signal gets too much downswing here, you bump into cutoff. But when the signal bump upwards, then horizontal wise, it try to bump into the saturation region. You also want to avoid. So that VCE must be above VC set. You really don't want to bump into the dead end. And if you want to set a margin, you can set a margin. So that's avoid saturation. And limitation, avoid saturation. And if you say your limitation could be coming from the downside current swing, that means when the crescent point is set a little bit low, it's not that in the middle, but somehow, unfortunately, crescent point out of here, then that portion of limitation sets what? Cutoff. So the full swing is a delta IC, and half the full swing is a downwards half swing equal to crescent point current minus the minimum, the full current I can tolerate. So that's this amount. So you figure out the amount of the swing I can expect from the current. Then you can translate into amount of swing on the VCE by this AC low line slope. That's one consideration. Another consideration is what? Coming from limitation from the saturation region, the point. That's when if the crescent point is unfortunately set a little bit high. So this swing, although you're not worrying about the cutoff, but you worry about you bump into this saturation dead end. So there's another way to evaluate the range. In this case, the evaluation is on the VCE, and that means a VCEQ minus VC minimum. So this VCEQ minus VC minimum is a delta, half of delta VCE. We can find out this limitation on the swing. And that's this equation. And by the AC low line, if you figure out this amount of voltage swing, you can figure out corresponding the current swing. And here subscript I use A and B really just says this is consideration A and this is consideration B. And what's the final one? Well, you don't want to, okay, if one happened early than the other one, you have to pick up the happen early one, so that swing of IC current should be the minimum of this above 2 consideration. Whatever gets smaller, you get smaller. And then likewise, you can get the same determination on the voltage VCE. Is still the minimum of these 2 evaluations. So basically, you have to evaluate. If I consider cutoff side consideration, I set the range. And if I consider the saturation side consideration, I set the range. And you want to see which range is large, which one is small. Of course, you can only go to smaller one because that sets the final undistorted amplification range. And you can also always verify the say upswing, downswing you may go to as much as here, upswing you may set it somewhere here. But if upswing somewhere here, then you cannot go downswing up here. You can only say if upswing is this portion, downswing will be this portion. A similar concept will be the voltage. And always saying, well, on the symmetric swing, so the upswing amount equals the downswing amount, then the quiescent point current will be just an average of the up current to the minimum current divided by half. So these 2 expressions always be true if you have a symmetric swing. And here, they are a little bit sort of abstract. So let's take an example. Take an example saying, if unfortunately the quiescent point is not in the middle and somehow tilted towards the lower side, along this low line is here. So that means what? Then this point is closer to the cutoff, but what? A little bit far away from what? Saturation. Our worry will be the distortion coming from the cutoff. So that means worry about the limitation coming from the cutoff side. And usually this is what happens is what? If the AC low line is slope is steeper, because AC low line is steeper, that means what? The low line, the upwards is further away from the saturation side, so you don't need to worry about that part, saturation. Okay, so if low, you can go as low as IC minimum. How much you can go upwards? The upwards will be the what? Questionable current plus add the half of the full swing. Okay. And what's the amount of full swing you can get? Half of the full swing is ICQ minus IC minimum, is this expression. So we will substitute this expression into here, then the final expression is this. So current can go as low as IC minimum as a margin. We don't want to touch 0, but it can go as much symmetrically on the upper side, get to this amount. Okay. And if we know the range of IC, then can we figure out the range of VCE on the on the right side and the downside, left side? Then you can calculate the VCE. Okay, minimum is VCE minus the half swing of VCE minus. And that swing we can calculate by this formula is swing of current multiplied by the resistance RC times RE. So that's multiplied. That swing, replace the swing by the current, and swing by the current is this amount, and multiply the resistance can tell me how much to the left VCQ can swing. How much you can swing to the right, then instead of subtraction this amount, I add this amount. So the second expression is identical, except the change the sign from minus sign to plus sign. Okay? So this is one example. Any question? This is a more general situation. Okay, illustrate, okay, there's a low resistance connected to the circuit. So basically, these are more like realistically, generally what happened. You have a biasing voltage V plus, V minus. You have an input source voltage coupled through the amplifier circuit by the capacitor CC. And you can second capacitor. Okay, actually here I choose this should be more popularly it's called CC1, CC2. All right. So and then coupled to the load. Coupled to the load means what? I don't want this load resistance influencing the biasing point. So I want to use a capacitor to block the road by the RL. But in the AC circuit, the small signal get after amplifier should be low to the low resistance. So that full circuit, just say the rest is the same to the left of this capacitor. To the left of the capacitor is the same as the previous one. So it's exactly the same as this part. All right. Only thing is now we have to take into account the role played by the load resistance RL. Okay, once
A
this
quick
capacitor
question.
is yes.
Can you repeat what the capacitor just did?
Okay, this is the AC equivalent circuit. All right, capacitor function. The role is sort of a coin of two sides. Okay, one side, what's the effect on the DC part of signal? The another side is what's the effect on the AC part of signal, right? Get it? Generally speaking. Okay, so it serves to block the DC signal. Or when you consider DC biasing, whatever, okay, to the left of this capacitor, you can neglect. To the right of this capacitor, you can neglect when you consider the DC biasing circuit. As well as this CE is open. So you have RE1, RE2 remain to the biasing point. For the AC signal, then we assume the AC's frequency is sufficiently high, so the capacitor becomes shorted. So capacitor is short, this is just a piece of wire. This capacitor is short, and we short out the RE2. When this capacitor is short, then RL is directly connected to this point. RL directly connected to this point. It's just set in. Answer your question?
Okay.
Huh?
Yes.
Yeah, it serves the two sides of the coin. Okay, what is the effect on the DC signal? What is the effect on the AC signal? For the DC signal, you block the DC signal, or you separate DC signal. So you separate means, or you separate this part of the circuit, you separate this part of the circuit, you move this, you're left with this part of the circuit. You do the question point calculation. For AC signal, all the capacitor can be treated as shorted unless we run into chapter 7. Okay. Before chapter 7, you can say in AC circuit, capacitor are shorted. But once capacitor shorted CC, then RL is set in. So the RL is set in. This circuit is modified from this previous circuit. So what the modification is, then you have a RC parallel with RL plays the same role as the original RC here. So the AC load line is modified with RC replaced by RC parallel with RL. Okay, and this AC load line slope. And slope, because it's a RL parallel with RC, the value should be what? Smaller than RC, so the load line slope will be even further steeper, get steeper. Okay, so it goes to the load line here. So this load line saying is the reciprocal of RC plus RE1. But if RC is parallel with another resistance, so that the denominator becomes even smaller. Smaller means what? The load line will become steeper. Okay. So that just say once you have a true full circuit, you have the load resistance. You also have to consider the role played by the RL. Any questions? Okay, so yep, that's all I want to cover today. Okay, so we'll pick up the new materials next class. Any question?
Oh, I'd like to let you know about a little trick I found out about WebEx.
Okay. Good.
It's a small thing, but when you click share content, there's an option where it says optimize for text and images. When you click it, there's another option to say optimize for motion and video.
Yes.
And when you click that option, there's less lag. So
That's lag. So that means that if I'm moving the cursor, it will be sort of better. So
yes.
right. Okay. Good to know that. I don't know how to take a balance trade-off that because most time with display the contents I display there. I don't know if I move to the other side, the other one, while the cursor moving to appear more sort of fluid and smooth. Will that affect the text or image resolution? I don't know. Do you know?
No, it won't.
It won't. So
Because you're showing a PDF.
okay. So so that trick we say my WebEx presentation I probably should select the video the mode right instead. So
Yes,
right.
that way your cursor doesn't.
It's not lagging.
It's
Right.
easier to do that.
It's not jumping something like that. Right. Okay. I will practice work that out. Okay, for the next class.
I'd sort of disagree because video mode makes it much harder to read text. If you